Okay, we're going to do some section 1.6 review problems. Okay, here's a problem like one of the homework problems. A car's skid mark, D, when it comes to when you slam on the brakes, varies directly with the square of the velocity V. At 30 miles an hour, the skid mark is 33 1/3 feet. What would the skid mark be at 50 miles an hour? Well, the first thing we have to do here is write a model for this. Well, it says the skid mark D varies directly with the square of the velocity V. Now, if it were just directly with V, it would be kV, but it's not just directly with V, it's directly with V squared. So our model here is D equals kV squared. Now we use the given information to solve for that value K. So I'm going to just round the 33 1/3 to 33.33 and plug that in along with 30 but squaring it to get 900. So 33.33 divided by the 30 squared gives us K, which is 0.037. So we can plug that 0.037 back in for K and we get D equals 0.037 V squared. That's what I call the completed model. Now we can use that model to answer other questions like what's the skid mark at a certain speed, or if we have a certain skid mark, what speed was it? And this type of relationship is actually used in law enforcement to see how fast someone was going. They do measure skid marks and use this relationship. So here our question is, what's the skid mark length when V is 50? So we just plug 50 into this completed model. So when we plug in the 0.037 or when we plug in the 50 in for V, square it times 0.037, we get 92.5, which I'm just going to round it to 93 feet because my K value is rounded here. So that's really the appropriate answer here. Just round it off. As you do this homework, however you round it, I'll accept the answer. So don't worry about the rounding too much. Okay, our next problem. The intensity I of a source varies inversely as the square of the distance D from the source. The intensity is I equal 80, and that's candle power. That's the units for intensity. When the source is D equals 10 feet away. What is the intensity at 15 feet away? So to do this, we need a model with K in it, and then we're going to use that given information to solve for K. So I varies inversely. What that means is I equals K not times D, but over D. If I varied inversely with D, it would be I equal K over D, but I varies inversely as the square of D. So it's I equal K over D squared. So there's our model. We can use the given information to solve for K in that model. So we plug 80 in and 10 in. So 80 is K over 10 squared. Then we solve for K, multiply both sides by 10 squared or 100. 80 times 100 equals K, or K is 8,000. So we get our completed model, I equals 8,000 over D squared. Well, now we can answer the question, what's the intensity when D is 15? So we just plug in 15 into the completed model. So when we plug in 15, we get 8,000 divided by 15 squared, or 8,000 divided by 225. 15 squared is 225. When we divide that out, we get 35 and it appears to be 555 repeating we just round that to 36 candle power. That's our answer. Okay, our next problem is a pendulum problem. For pendulums, the period, which is the time for the pendulum to go back and forth one time, one complete cycle, the period t of a pendulum varies directly as the square root of its length L. A pendulum 9 feet long has a period t equal 3.12 seconds. With this, we are to answer the two questions. What's the period of an 18-foot pendulum? And part B, what is the length of a pendulum with period of 6 seconds? Now, to do all this, we need a model. Just like the previous problems, we have to start with a model, and it says t varies directly as not L, but the square root of L. So our model is t equals k times square root of L. So now we use the given data. 9 feet long, we plug in 9 for L and 3.12 for T. So you have 3.12 equals K times square root of 9, and we solve that for K. So after we plug in 9 into our completed model, or I mean our uncompleted model rather, square root of 9 is 3. 3.12 equals 3 times k, divide both sides by 3, and we get a k value of 1.04. So our completed model here is t equals 1.04 times the square root of L. We can use this model to answer both questions A and B. In question A, we're just plugging 18 into the completed model. So when we plug in 18 into the model, we get t equals 1.04 times the square root of 18. And when we calculate that out, we get 4.4 seconds, which sort of surprising. We doubled the length of the pendulum, but it only increased a little over a second. Well, that's because it's proportional to the square root of L, not L. Now in part B, we want to find the length given the period of the pendulum is 6 seconds. So here we're plugging 6 in for t, and we're going to solve this equation for L. So after plugging in plugging in 6 for t, we divide both sides by 1.04. We get 5.769 equal the square root of L. Well, to get L, we square both sides. And here, when I square both sides using the 5.769, I get 33.2 feet for the length. So it's quite a bit longer length to give you that period of 6 seconds. And an interesting thing here is if I had not rounded the 5.769 on my calculator, my final rounded answer would have been 33.3 feet. So in this case, I should have probably carried another digit or two on that 5.769 in order to round up to the 33.3 feet. So that's just a point worth mentioning here. Okay, and that's it for the 1.6 review, and we'll see you in discussion or class.